Okay, problem number 1. We want to give the domain and the range of the relation. And then we want to answer, is this relation a function? So keep in mind that we have the domain being the first items in the relation, or the first occurrence. So for example, 11, 10, -8, and -8. So that would be the domain of the relation. Then the range is the items that happen in the second occurrence, or the values that go on the y spot. So 2, -9, 4, and -3. So if we write that out, we'll have the following. We have the domain be 11, 10, and -8. Then the range will be 2, -9, -4, and -3. Now, is the relation a function? And the answer is no, because -8 in the domain repeats. Okay, so that's the reason why it's not a function. Next, we want to determine whether the equation defines y as a function of x. So we have two examples for this, or two problems. And notice how in the first one we can rewrite number 3 as a function of y by itself, and it would be negative, 6y equals negative 6x plus 6. And if we further simplify that, we get negative 1x, or just negative x, plus 1, right? So we notice how y is defined as a function of x. Fairly straightforward. Now, for number 4, we don't have the same, right? We have y squared equals to 81 minus x squared. And if we solve for y, we have to take the square root of both sides, and we get y is equal to plus or minus 81 minus x squared. That means that there is two functions, the positive square root and the negative. So y is not defined as a single function of x. It is defined as two. One that's the positive square root, and then the other one that's the negative. Another hint is to look at the power on the y, right? If that power is even, then it is not. So we can say that number 3 is yes, y is defined as a function of x. Number 4 will say no, y is not defined as a function of x, and for the same reason that there's two equations, or because the power on the y is even. If it were odd, like in number 3, which is power 1, then we're good to go and we'll say yes. Okay? Next, we want to use the vertical line test to determine whether the graph, or whether or not the graph is a graph in which y is a function of x. So pretty much we're asking, does the graph pass the vertical line test. Meaning that if I was to run run a vertical line all the way from the left to all the way to the right, does the vertical line only touch once? And the answer is no, right? Because there are several places where my vertical line touches the graph of the function twice. So, in other words, no, it doesn't pass the vertical line test. But what else does it tell us? It tells us that the graph is not defined, or it doesn't define y as a function of x. Okay, so that's the two things that it tells us. Overall, it's just one thing, but you can look at it different ways. So the graph does not define y as a function of x. Okay? And then here is the same directions. Can we run a bunch of vertical lines through this graph? And does it pass the vertical line test? And does it define y as a function of x? And the answer is yes to both, right? So yes, it passes the vertical line test, and yes, it defines y as a function of x. Okay? It passes the vertical line test because it only touches once or intersects once the graph of the function. Okay? Next, we want to use the graph to determine the function's domain and range. Okay, so look at the domain as the values of x where the graph actually happens, right? So if we look at it, the graph is happening all the way from the left to all the way on the right. Then the range is going to happen for the values of y. So with respect to the values of y, or with respect to the y-axis, where is the graph? Where is the graph happening? So up here, and then we get all the way down to the value -4, and it doesn't happen anywhere below that. So how do we write the domain for this then? So domain is all the values between -infinity and all the way to +infinity, right? That's my yellow highlighted line, right? Then what is the range? The range happens from the bottom up, so exactly starting at -4 and then going all the way up to +infinity is where my range happens. Okay? That's it. Again, for number 11, the domain is where the y values, or with respect to the y-axis, where the graph is actually happening. So starts here at 0 and goes all the way to the right endlessly, right? It doesn't have a stopping point. And then the range starts at -2, and then it goes all the way up. And we assume, although it's not shown on the graph, that the graph goes on forever. So it goes on forever to the right, so in the positive x direction, and then upwards in the positive y direction. So domain is going to be from 0, starting at 0, all the way up to +infinity. And Why do we put a square bracket? Because of that solid dot that is at the value x equals 0. Then the range starting at -2, because there is a solid dot at -2, and then going upwards all the way up to positive infinity. Okay? Then we want to graph the given function. So notice that it has a power 2, so it will be a parabola. So if we draw just the parent graph or the common graph, we see that we have something like this, right? That's the parent graph. So pretty much what's happening is that there is a negative in front, so we want to keep that in mind, that that's a reflection over the x-axis. Then we have a transformation 2 units to the left and then 4 units down, right? So think of the center point 0, 0 being pushed to the left 2 units and then downwards 4 units. So therefore it's somewhere over here and then being flipped downwards or over the x-axis. So the green will be the graph of the function that we have there, negative x plus 2 squared, and then all of that minus 4. Okay? Again here, we're given to graph this function, and notice that we have the negative in front, which means a reflection over the x-axis. Then we have a transformation to the left, 2 units, and then downwards 1 unit. So let's go ahead and graph the parent graph or the parent function. And it looks something like this, right? It starts at 0, and then it goes all the way to the right. So let's think. It moves to the left 2 units, and then downwards 1 unit. So it'll be over here. And then since it's been reflected over the x-axis, it's going to look something like that, right? It just kind of opens downwards, but it goes in the same direction to the right, okay? Next, for the given functions f and g, we want to find the indicated composition. So if it's not clear, we're looking for f composed of g at the value 9. So one way to look at this is the following. The function f composed of the function g evaluated at the value number 9. Well, one easy way to do it is to plug in the 9 into the g. So let's do g composed of 9. So that becomes 19 times 9 minus 4. So we have 19 times 9 will be 171. Okay, so g composed of 9 is 167. Then whatever that is, so this right here is equals to that, we are going to plug it in into the function f, and then we have 9 times 167 squared minus 5 times 167. So you have to be careful and notice that function f has 2 places where the x happens. So you have to plug in the value into both of those. Okay, so maybe I'll just write it up here, and so that you see it, we have Okay, 9 times whatever g of 9 is, all of that squared, minus 5 times whatever g of 9 is. Okay, so at this point it just becomes a calculator problem, and you plug that into the calculator, making sure that everything that you plug in is correct. Some parentheses around those numbers will be very helpful, and the answer comes out to be 250,166. Okay. Next, we're doing g composed of f and at x. Not really any number in particular, but just of x. Okay, so what happens is that we have the function g, which is 3, and we're plugging in the function f of x into it. So 3 times f of x minus 3. So this time we're doing the same thing. We're plugging in f into the g. Well, it just follows from there that I'm going to replace the function f with what it is. So 4x squared plus 3x plus 6, and then all of that minus 3. So at this point it's just simplification, really, right? We're just simplifying the problem that we have there. So 3 times 4, 12x squared, then 3 times 3 times 3, 9x, and then 3 times 6, 18, and then don't forget to keep bringing down that minus 3 or those extra items on every step. So now we just combine like terms, 12x squared. The x squared doesn't have any like terms, so we just bring it down to the next step. 9x doesn't have any like terms, so we'll just bring it down. And then 18 minus 3 will be just 15. So that will be the composition g composed of f. Okay, this is the solution. Next, find the inverse of the one-to-one function. Okay, so remember, step 1 is to turn the f of x into a y, simply so that it is easier for us to tell the variable apart instead of the f of x. Step 2, we're going to swap the x and the y, so 2y minus 1 over 7, and then now we're going to solve for y. Again, we swap them and then solve for the other function, for the other variable. So we have 7x equal to 2y minus 1, and then at this point we're just solving for 1. Oh, okay. Seven x plus 1 equals to 2y, and then divide both sides by 2, and 7x plus 1 over 2 is equals to y. And the very last step is to change this y into f inverse, or f of x, but to the power -1 if you wish to call it that. But just keep in mind that it is notation. It doesn't mean f to the power -1. It just says this is the inverse of the original function f. Okay? Alrighty, next. Use the graph of f of 5x. So the graph of 5x goes through the point 0, 1, and it looks something like this. Let's see. It goes through that point, and what we want to do is find the graph of 5 to the power x minus 3, all of that plus 2. So just like with the other functions, there's a shift to the right by 3 units, and then a shift upwards of 2 units. So from that point 0, 1, we're going to go to the right 3 units right here, and then up 2 units. So right there, meaning that our graph is going to look something like this. It'll go through that point again, so and the green line will be my function g of x. Okay, similar in shape to the original function, it just has been pushed to the right and upwards several units. Okay, again, just finding the graph of an exponential function, then we want to use the parent graph e to the x, and e to the x as well goes through 0, 1, because e to the 0 power equals 1. And we look at the graph g of x that we're asked to plot, and there's been a shift to the left of 4 units, and then downwards 3 units. So we want to follow that 0, 1 point to the left 4 units, so right here, and then downwards 3 units, which is right there. So something like this, right? My graph is going through that point and then shooting upwards. So when we do it on the computer, it'll look more accurate, but at least we know what the transformations that happened were. Okay, that's the most important part. Next, we want to use the compound interest formula. There are 2 of them there, so we have to choose which one to use for the problem that we have there. So since the problem is saying compounded quarterly, right, it's giving us some value for the compound other than continuous, then this right here gives it away and tells us to use this formula. Okay, so let's define everything that we are going to use before we start. So P, which is the principal or the initial amount, is 1200, so that'll be our P. The rate is the amount by, or the value that it's increasing by. And in this case it's 10%, but we have to turn it into a decimal. So 10% divided by 100 is decimal 10 or 1/10. N is how many times is it being compounded per year. And quarterly means it happens 4 times per year. Time, how long, or for how long is the investment being accumulated, and it's for 2 years. So then we're good to plug in, and we have A, which is the amount or the accrued interest amount that will equal after 2 years. So 1200 times 1 plus the percent rate, the interest rate, divided by the number of compoundings to the power number of compoundings, which is 4, times 2. So at this point, just Either do it by steps where you are adding the inside, and simplifying little by little, or just go ahead and plug it in your calculator all at once if you're confident that it will come out right. And if you don't feel confident, then do it like I'm doing it here, step by step. Make sure to not round so much at every step so that your answer becomes less and less accurate. Okay? So I got 1462 decimal 08. So I feel like that's a good answer. Round to the nearest cent, and I didn't lose too much accuracy since I didn't round off too much at every step. Okay. Next, we want to find the accumulated value of an investment of $2,000 at 9%, compounded continuously. So continuously tells us use the other formula. Okay. What is the other formula? The other formula is the one that goes A, or the accrued amount, equal to the principal times the number E raised to the power R times T. That's the formula for when things are happening continuously, pretty much. So let's go ahead and define our values. The principal is how much money we start with, or the initial amount. Then the rate, which is 9%. Turn it into a decimal, is 0.09. And time is going to be 4 years. So let's plug that in, and we have A is equal to 2,000 times E to the power 0.09 times 4. So plug it in the calculator or do it little by little. Okay, and as you feel more confident about typing in the calculator everything at once, then you will, and if not, just do it step by step and make sure not to round off so much at every step so that your answer doesn't become way off. Okay, so even though I rounded a little bit at the end, it will still be accurate enough, and this will be our answer. Okay. Okay. Write the equation in its equivalent exponential form. Okay, so we're going from logarithmic form to exponential form. It's important to recognize at least what form are we starting with, right? And there's only two, right? Logarithmic form and then exponential form. So it's not too bad. Just remember that we're going to use that trick of the arrows where we have, in our case, 4 is the base, so 4 raised to the power, and then all of that equals whatever is in the argument of the logarithm. So That means the following: 4 to the power 3 equals x. And this is exponential form. Okay, so if you keep that in mind, it'll help us solve many other problems later on. Okay, that's our answer. We don't have to simplify because otherwise it won't be in exponential form. Okay. Okay. Next, we want to write the equation in its equivalent logarithmic form. So we are given something in exponential form, and we are going to the logarithmic form. So 2 to the power -2 is equals to 1/4, and we want to turn it into a logarithm. So I'm just going to go ahead and write the word log because I know I will need it, so I might as well start off with that. Then, what is the base on this problem, right? So base is 2. The exponent is -2. So the base goes in the base. So both places, exponential and logarithmic, have the same place for where the base goes. Then I like to put the equal sign just because I know it's going to be there. And then I think to myself, 2 to the power what? So it's kind of working backwards as if I was going from logarithmic to exponential, but I already have the exponential form. So I'm just trying to rewrite it. So 2 to the power -2, right? Because that's the exponent. So think of this as the base exponent, and then the only place that's left is the argument. So 2 to the power -2 gives me -4. And so it matches my exponential form that I have. So therefore this is my corresponding logarithmic form. Okay, hopefully that makes sense. Okay, next we want to use the graph of log base 5 of x to graph the function log base 5 of x plus 2. And also draw the asymptote as a dashed line. So where is the original function really happening? It goes through here, through the point 1, 0, and then it goes to the right and upwards, and it has a vertical asymptote at the function x equals 0. So if we look at the given function, this has a shift to the left of 2 units. So it goes through here. Okay, so if we graph it, it looks something like this. And one way to find the asymptote is get the argument, set it greater than 0, and solve for x. So this will be where our asymptote is. So pretty much think of it as the equation x equals -2, because the function will get really close to -2, but it will not touch it. So that's where that vertical line is. And also that helps us with the domain, right? That will be the domain of the function as well. Okay. Find the domain of the functions. So like we were just saying, it doesn't matter the base. of the function. What we want to do is get the argument. Whatever's inside of the parentheses is called the argument. We want to get that value and set it greater than 0. And then solve for x. So x plus 1 greater than 0. Solve for x. X is greater than negative 1. Perfect. So the domain tells us that from negative 1, not including, all the way up to positive infinity. Okay? That would be the domain of the function. Then, for the other one, it's a little bit trickier, but setting it greater than 0 helps this, I guess, be visualized easier. So 5 is greater than x. So if it doesn't make sense to you, flip it, right? Reverse the order and graph it on a number line. So where can there be values that are less than 5, right? Because x can take any value. So where are those values true? And it happens to be this way, right? Below 5. Not exactly 5. So here is negative infinity all the way up to 5. Okay? If you're coming from the left, you start at negative infinity and go all the way up to 5, and that's where the domain of this function is, as compared to from one number to infinity like it was on number 41. So, and the reason is because there's a negative in front of the x. So it pretty much has been flipped to the left side. Okay, so setting it to greater than 0 will solve that problem from the beginning. Okay. Okay. Use properties of logarithms to expand the logarithmic expression as much as possible. And then where possible, evaluate the expression without using a calculator. So, in the argument, which is inside of the parentheses, we have a product, y times z to the power 8. So that means we'll have log base b of y. I mean, you could put in parentheses or without parentheses, as long as you know that that's the argument. And then the product becomes a plus. Log base b of z to the power 8. So we're not done. We can simplify this one step further. So log base b of y, it's already as simple as it can be. However, we could bring this power down to the front, and that's the next step. So 8 times log of b of z, and that would be as expanded as it can be using the properties of logarithms. Next, we're doing the same thing. We want to expand as much as possible the given logarithm. So, first thing we'll break will be this quotient. And remember that when we have a division inside of the logarithm, it's going to become a subtraction. So, log 11 of the 7th root of 3 minus, and then put it in parentheses, right? So minus log base 11 of y squared times x. And I put it in parentheses just so that you can see the next step, so it makes more sense. It illustrates it better visually. So 2 steps at once. I'm going to do log base 11 of 3 to the power 1/7. Okay, so the 7th root becomes power 1/7 minus log base 11 of y to the power 2 plus log base 11 of x. So we have just split that product into a sum, but still keeping it inside the parentheses with that minus outside. Then I'm going to do a couple things at once. Bring this power to the front, bring that power to the front, and distribute that minus that's outside. So 1/7 times log base 11 of 3 minus 2 times log 11 of y minus log base 11 of x. Okay, and that's as simple as I'm going to leave it. Next, we want to use properties of logarithms to condense the logarithmic expression. Write the expression as a single logarithm whose coefficient is 1, and where possible we want to evaluate the logarithmic expression. So to start, we want to bring the number in front up as a power. We're using kind of the reverse property that we just did a second ago. So this is going to look like ln of a to the power 4 minus ln of b to the power 7. First step. Then notice that there is a minus between the two logarithms, which actually have the same base. They're the same logarithm. So it's just going to be a division or a quotient. So a to the 4th goes in the numerator since it happens first, reading it from left to right. And then b to the 7th power goes in the denominator. And that's it. We have condensed it to one logarithm using the properties of logarithms. Next, we have this little complicated one because it has more parts to it, but not too difficult. So first thing, the number in the front goes up as the power, and then we have the following: log base 6 of x to the 3rd power plus log base 6 of x minus 6 to the 5th power. Then we notice again that we have a plus, so that tells us that there will be a product. Log base 6, we can condense it since they both have the same base, so this becomes x to the 3rd times x minus 6 to the 5th power, and that's it. Next, we want to solve the equation by expressing each side as a power of the same base and then equating the exponents. So the base here is 25 on the left and then 125 on the right. So the trick is to write 25 and 125 as the same base. They're not necessarily equal to each other, but those were the two bases that we have in question. At least that's what I want to show. So 5 to the power 2 is the same thing as 25. So at least that's the first guess, right? You have to start somewhere. And then 5 to the power 3 is 125, and then x minus 7 is the exponent. So notice how we have gotten the same bases, really. So 5 is the base, okay? Then we make use of the power to a power rule. So 5 to the power 2 times the exponent x plus 10. So make sure you apply correctly the rules of powers of exponents in order to simplify this. So now that we have the base by itself, and notice that it is the same, so there are 5s and nothing else inside of that parentheses, we can safely just discard them. Now, there are reasons why we do that, but you get rid of the bases and set the exponents equals to each other, and then just solve, right? So 2x plus 20 equals to 3x minus 21. So take away 2x on both sides. And then add the 21. And then we have our x being equal to 41. So if you ever have questions, feel free to plug the number in there, and the left side should equal the right side, okay? And, also on here, because that's the x value that works for that equation. Okay, next, solve the equation, the exponential equation, and then use a calculator to obtain a decimal approximation, correct to 2 decimal places for the solution. So a couple ways to do this problem. First will be to apply ln on both sides, if you will. So if you do that, you get the following. Ln of 10 to the power x is equals to ln 4.51. Okay. Then we use the power property to bring the x to the front. And we have x ln of 10 equals to ln of 4.51. So next, we would divide both sides by ln 10, and x is equal to ln of 4.51 divided by ln of 10, and that is a exact answer because I haven't really plugged into the calculator or solved anything, so it is pretty accurate at this point. But once I put it in the calculator, it becomes an approximation. So let me wait to the last step of the other way to solve this to show the final answer. So notice that we have 10 to the power x equals 4.1, so 4.51. So that is a exponential equation. We can write it as a logarithm. So log base 10. So 10 to the power x equals 4.51. So if we plug in log base 10 of 4.51, we get the value of x. And notice that if you just do log of 4.51 without any base, that is the common logarithm, right? So those are two ways to get the same answer. And so let's see, whether you plug it in this way or this way, they're both going to give us 0.65. So 2 decimal places, 2 decimal places. And they both give us the same answer, okay? Here again, e to the power 2x is equals to 6. So, two ways to do it again. Apply ln to both sides. Bring the power down. In this case, the power is 2x. So 2x times ln e equals to ln of 6. And maybe you have or maybe you haven't. Notice that ln of e is 1, but if you haven't and you're just pushing along the problem, you divide both sides by ln e. You have 2x equals to ln 6 over ln e, and realize that ln e is just a 1, so I'm gonna just drop it, and then we'll have that x is equal to ln of 6 divided by 2. So what if I do it the other way, where I just rewrite it as a logarithm, and I say log base e of 6 is equal to 2x. So e is the base, 2x is the power, and 6 is the argument, right? And then log base e is equivalent to ln, and so we just pretty much come back to the same thing. So if we plug that into the calculator, ln of 6 all divided by 2, we'll get the following: 0.90. If we round to 2 decimal places. Okay. Next, solve the logarithmic equation and be sure to reject any value that's not in the domain of the original function. So give the exact answer. So let's combine and do the best we can here. So notice that we have two logarithms separated by a plus, but they have the same base. So what we need to do is combine them into one logarithm and really just try to get rid of the logarithm. So log base 3 of x plus 4 times x minus 2 all equals to 3. So now I have a single logarithm, and I can just easily rewrite this as 3 to the power 3 to the power 3, right? Because this is the 3 raised to that equals to the other thing, or what's in the argument. So equals to x plus 4 times x minus 2. So we have 9 equals to x squared plus 2x minus 8. Four x minus 2x gives us 2x. I think that's correct. So at this point, we're going to move the 9 to the other side. So x squared plus 2x. And so negative 8 minus 9 is 17. Uh-oh, same mistake. Sorry. So 3 to the power 3 is 27. So we have negative 8 minus 27, and that gives us 35. So we're going to factor this, and we have two numbers that when you add them together give you 2, or two numbers that are 2 units away from each other, and when you multiply them, give you 35. So xx, and then 7 and negative 5. So now that they're being multiplied to each other and it equals 0, we'll make the zero product property, make use of it. That's what I'm saying. X plus 7 equals 0, x minus 5 equals 0, and so we get x equals to negative 7 and x equals to 5. Perfect. So those are our two possible solutions. Now, which one of those will work or won't work? We have to try them by plugging them into the arguments of the original. So negative 7, if I plug in negative 7, we'll get negative 7 plus 4, and just even check it on one of them. What's negative 7 plus 4? We'll get log 3 of negative 3, and we cannot have a negative number inside of the argument because that's outside of the domain of logarithms. So right away we can say negative 7 is not a good answer, and x equals to 5 is a good answer, and on top of that is the only one left. So x equals 5 will be the answer for this problem. Okay, next we have log 3x is equals to log 5 plus log of x minus 2. So many logs going on here. What we can do is combine the right side. So log 3x, notice that they have no base, so that means the base is 10. This is the common logarithm. So we'll do log of 5 times x minus 2, and then log 3x equals to log 5x minus 10. So at this point, we can do a couple of things. If you understand, I guess, they both have base 10. So what I can do is raise both left and right to the power 10. So 10 to the power log of 3x is equals to 10 to the log 5x minus 10. And since this base and that base are the same, then they cancel each other out, and we'll be left with 5x minus 10. So that's one way to solve it, and we'll get that. We'll move the 5x to the left, and we'll get negative 2x equals to negative 10. And then we have x is equals to 5. Right, so, but if maybe from this point on it was confusing, we can do log of 3x minus log of 5x minus 10 equals 0. Notice that they both have the same base, so we can say log 3x over 5x minus 10 equals 0. And single logarithm, we can turn that into an exponential. Base 10 to the power 0 equals to whatever's in the argument. So 3x over 5x minus 10 is equals to 10 to the power 0. Just turn it into an exponential. 10 to the power 0 is just 1. And then now I multiply this to the other side. So I have 3x equals to 5x minus 10. And then we work that out, and x equals to 5 again. So pretty much here it meets where that is equal to itself. So two ways of working it out. One was 10 to the power of raising both sides by base 10, or 10 to the power of both sides, or just doing it the other way where we combine logarithms and show a different way to do it. Okay? Here, since we have both same bases on the left and the right side, we can do the same thing as we just did. So 9 raised to the power log base 9, so like this. But if we notice that they're both the same, we can just drop them, and we'll get 4x minus 3 equals 2x plus 4. So the middle step is just to show you kind of what's going on. But if you notice here, log base 9, and that's it. So you can just drop both the logs and go from there. And that's it. Okay, we're getting into figuring out how long something will take for it to grow, right? Like in this case, the interest formula. So find out how long it takes a $3,200 investment to double if it is invested at 8% compounded quarterly. So round to the nearest tenth of a year. And we're told to use that formula. So, well, if P is the initial amount, right? So P, $3,200. The investment rate is 0.08. T, we are looking for it. We don't know. N equals to 4. But unlike the previous problems, we now know the value of A. The value of A is twice of the initial amount. Only because we're looking for how long it takes for it to double. So A is equal to 6,400. So from there we can divide both sides by 3,200. We can apply ln to both sides. And then now that we have it in terms of a logarithm, we'll bring the power down and have ln2 is equal to 4 times t times ln of, and then perhaps this in here we could simplify so that we don't have to keep writing the same thing. Okay, And so the next step will be to select the things that don't belong with t and divide by them. So divide by 4 ln of 1 plus 0.08 over 4 on both sides. Therefore, t is equal to ln of 2 over 4 times ln of 1 plus 0.08 over 4. So at this point, I recommend solving little by little to simplify that, or if you feel very confident into plugging this into the calculator, then go ahead and do that. And we get t equals to 8.75, but we're supposed to round to like about 2 decibel to the nearest tenth, so 8.8 years.